Welcome to Control System classes from Electrical Engineering Talk. So today's topic under discussion is effect of zeros and its contribution to the first order systems. How will you define zeros? How will you get the zeros? The roots of numerator when it is equated to 0 will give the solution as zeros. So let us consider a simple transfer function C of S by R of S as 1 divided by S plus 1. So the 0 is going to be placed at minus 1. So the 0 is placed at minus 1 for the given S-plane representation. As the 0 is placed there, so what would be the time response? The time response will be like this, right? So when let us introduce a 0. So the 0 is introduced at minus 2. So now the transfer function becomes S plus 2 divided by S plus 1. So what would be the plot? The plot will have the changes in transient response and it will not start at origin. The plot will not start at origin. It will start with the initial magnitude. Now let us move the 0 far away from the imaginary axis. When it is moved far away from the imaginary axis, the effect of 0 to the system is less and hence it will contribute only the lesser magnitude in the initial transient portion. Let us assume the zeros are shifted to RHS. What would be the effect? So let us introduce a 0 at S is equal to 2. So the transfer function is S plus S minus 2 divided by S plus 1. As it is S minus 2, in the magnitude will have the transient portion will have started positive side, then afterwards it will crosses the 0, then that is the 0 axis, then it will move to the negative side. So it creates an undershoot. The zeros on the RHS will create an undershoot. Similarly, let us assume a 0 at S is equal to 20. So it will also create an undershoot, but the effect of initial magnitude will be less when compared to the previous case. So this would be the shape of the effect of added 0 at S is equal to plus 20. What would be the contribution if a 0 is added at origin? So let us assume I have the function S divided by S plus 1. When I have S divided by S plus 1, it is nothing but a differentiator. So I have added a differentiator. What is the effect of differentiator? When you differentiate a constant, it will become 0. So wherever there is a changes, you look at the first plot, the changes are during only the initial portion. Afterwards, the final portions are constant. So it means over the initial portions will have a change, will have the changes in the plot, then I will have a 0 in the plot. So this would be the plot of various locations of 0. So what is the conclusion? I'm going to verify the same concept with numerical examples and with MATLAB program. We will try to verify the concepts now. So what is the final conclusion about the present slide? So the 0 will increases the speed of response and it reduces the rise time. It affects only the transient response and it creates an undershoot or overshoot. When it will create an overshoot, for example, when you keep a 0 very close between, let us fix a 0 between 0 and minus 1. During the time, it will create an overshoot and the plot may have an initial amplitude more when compared to the previous case, but it will not affect the steady state value. It will be the same. So this will create an overshoot. As it is greater than my final value, this portion is my overshoot. But when my zeros are to the present to the left of my pole, it is present to the left of my pole, it will not create an overshoot. So this is the concept you need to observe here. So let us verify the slide with respect to the concepts and MATLAB programs. So let us how to create C of t. Let us learn with a simple example. C of S by R of S is 1 divided by S plus 1 and I am going to consider my R of S as 1 by S. So my equation is C of S is equal to A by S plus B divided by S plus 1. So on solving with partial fraction calculations, I got AS1, BS minus 1 and as I need the value of C of t, I have taken inverse Laplace transform. So 1 by S on taking inverse Laplace transform will become 1. 1 by S plus 1 on taking Laplace transform, it will become e power minus at. A value is 1 here. So now I'm interested to calculate my initial value. How to calculate my initial value? You need to substitute t as 0 in this equation. So I'm going to substitute t as 0. When I have substituted t as 0, e power 0 is 1. So 1 minus 1 is 0. So my plot will start at origin, right? So let us calculate my final value by substituting my t as infinity. Let us substitute t as infinity. So what is e power minus infinity? It will become 0. So e power in minus infinity is 0. My final value would become 1. So it means my plot will settle at a final value of 1. So this is a plot without adding any zeros, right? Now what is my error e of t? E of t can be calculated as difference between r of t minus c of t. What is r of t? R of s is 1 by s. R of t is nothing but 1. So 1 minus the obtained function c of t will give my value e power minus t. So how to calculate ESS? We know the formula of ESS in time domain is limit t tends to infinity e of t. So substitute t as infinity, so it will become 0. It means when unit step input is applied to the function, it will respond without any steady state error. For ramp input or parabolic input, there will, according to the given nature, there will be error. But for step input, it will respond without any error. In this slide, let us discuss about the effects of zeros in LHS and RHS and with a special case. So for that, I have tabulated the given function, the assumed transfer function is given as t dash, t dash 1, t dash 2 and so on. So the first two cases, the zeros are located at LHS, then RHS, then at origin, special case. To calculate the DC gain, substitute SS0 as we had substituted SS0. It is 2 by 1, 2, 20 by 1, 20, minus 2 by 1, minus 2, minus 20 by 1, it is minus 20 and so on. So here when you substitute SS0, 0 by 1, it will become 0. So now my question is, I cannot able to compare the effect of 0 as my gains are different. So I need to normalize my DC gain, that is my final value. DC gain is also called my steady state value. I want to normalize my final value. For that, to the given transfer function t dash, I'm going to multiply it with by p by z. It means I'm cancelling the effect of change in DC gain. So p is 1 for the first case and z is nothing but 2. So p by z is 1 by 2. Similarly, for all other case, I had multiplied it with by respect to p by z. So now, when you substitute s is 0, here 2 divided by 2, my gain is 1. Here 20 by 20, my gain is 1. Here minus 2 by 2, my gain is minus 1. Here minus 20 by 20, my gain is minus 1 and so on. Now I have got my normalized gain. Then I'm going to calculate C of t by taking inverse Laplace transform. I'm going to take inverse Laplace transform. So by using partial fraction, the given C of t is calculated. Now I'm interested to calculate about the next step, initial value and final value. So to calculate the initial value, I have substituted t as 0 here. So when I have substituted t as 0, my initial value is 0.5. In the next case, when I had substituted t as 0, it is 0.05, 0.5, 0.05 and 1. Now I have calculated the initial value. So from the initial value, what you observe? For the first case, what we had discussed, without adding zeros, my initial value is 0. But in the first case, T1, my initial value is 0.5. When the 0 is far away from the imaginary axis, my initial value is reduced. So what you understood from it? So instead of starting at origin, there is an initial magnitude. It means it increases the speed of response and the rise time is decreased with added 0. Now, what would be the case if a 0 was added at RHS? So, for the first case, the initial magnitude is 0.5. My initial magnitude is, for the second case, 0.05. Initially, it looks like it is good. Let us observe what would be the effect of 0 at RHS. Let us calculate the final value. To calculate the final value over this expression, substitute t as infinity. When you substitute t as infinity, 1 minus 0.5 e power minus infinity. E power minus infinity is 0. So final value is 1. It is same as set of DC gain. My final value is 1. My final value is minus 1 and 0. So what would be the case? So here the graph starts at 0.5 and it goes in the right direction and settle at 1. Here the graph starts at 0.05 and it settles at 1. Here the graph starts at 0.5 and it undershoots, it crosses 0 and settles at -1. Here the graph starts at 0.05, again undershoot and it reaches -1. Here starts at 1 and it will reach as 0. So what is the concept we can say here is there is an effect of undershoot when a 0 is added to the RHS. Similarly, when a 0 is added at the LHS, it will increase as an initial magnitude and improves the speed of response by reducing the rise time. Right? So similarly, we can calculate E of t and ESS as like that of our previous case. So what is the final conclusion from this slide? There is a change in transient portion and not in the steady state value. And also it contributes initial magnitude and it increases the speed of response and reduces the rise time. Let us move to the next. Let us look at the MATLAB program execution with added zeros. So here a simple MATLAB program is given. CLC clear all, close all. These are the initial commands to clear all the workspace values, command window functions, and also close the previous operated figure window and to open the new figure window. And in order to write the function in S domain, I have used S is equal to transfer function of S. The transfer function of all the cases without zeros, with zeros on RHS and LHS is given. The DC gain of T will calculate the DC gain or final steady state value. I want to plot all the graph in a single figure window. I have given the command step of all the transfer functions, comma 5. Here this 5 represents the time of the overall time duration of the plot. It means the graph will plot from 0 to 5 seconds. Then the legend will represent the notations. That is, it will print the graph on various colors, and for each color, it is a plot. It will represent the respective plot. Blue represents what plot like it will represent. And also DC gain, as the semicolon is not fixed, given for a DC gain, it will print the output of DC gain of each transfer function. So when you executed the script file with MATLAB, so you will get the DC gain like that. It represents the final steady state value, what we have already shown in the previous cases. Now let us see the output waveform after the execution of the program. So here 6 plots have been shown here with 1 at origin and 2 at LHS and also 2 at RHS and 1 is without any zeros. So here the first plot, this blue represents, it is a graph of the given first order system without any added zeros. So the graph plot will start at initial value and it's gradually increases and settles at the final value. Now let us consider S is equal to -2 as it is close to the origin. When the 0 is added close to the origin, it will contribute a larger transient. It will contribute a larger amplitude in the initial case. So it affects the transient state and it starts at 0.5 and then it reaches a final value. Similarly, a 0 at S is equal to -20 which starts at 0.05, gradually increases, settles at final value 1. What about the remaining cases? The remaining cases will settle at -1 as we had normalized the gain in the scale of 1 or -1. But what would be the initial amplitude? The 0 nearer to the imaginary axis will start at higher magnitude. So it means it will start at 0.5. The pole far away from the imaginary axis at L is equal to +20 will start at 0.05. And this blue represents the plot that corresponds to a differentiator. So it means S divided by S plus 1, as it is a differentiator up to the transient duration, it has an output. It has some variations in the plot. Afterwards, it is settling at the final value. So this is the concept what we can able to verify with the previous what we had verified in the same answer with the previous theoretical concept. So theoretical concept and practical concepts were matched. So thank you. Thanks for watching the video.